So normally before LCA, I come back to the venue and set up a lot of recording stuff in a thing we call the TimVideo Hackfest. And the idea is to get the recording all working really well, but because, open source is not really normally deadline driven, we actually get everything working the week before the conference. However, this year I wasn't able to attend that, so like Hackfest, which has my name in it, didn't have me at it. And the reason was I was at this event in Salt Lake City because in the US, they have a new DARPA initiative called the Electronics Resurgence Initiative, which is what this ERI thing down the bottom is. And I was giving these 3 talks at that conference for the attendees. If you haven't heard of this program, it's a pretty cool program, and there are 2 specific really cool things in it. They're trying to build basically a fully open source toolchain for making ASICs. So if you want to make an actual chip, at the moment, you use Cadence or Synopsys tools. Both those are highly proprietary software that kind of have seat licenses that start in the 150K per seat license type range. And so for some reason, DARPA is funding tools which should let you do the same type of thing without needing to pay for them. And they're also funding the development of a whole bunch of cores to give you like a standard library. So they're trying to create like the GCC of ASIC world and the glibc, but they're not particularly, they're mostly academics. They're not particularly open source knowledgeable. And one kind of hole is that they have to concentrate on actual research. They can't actually do software engineering. And the reason I was there is because my employer cares about making ASICs. They're very famous for doing the TensorFlow processing unit, which is an ML thing. But the problem is most commercial people use this thing called SystemVeryLog, and the open source tools only support Verilog. But adding SystemVeryLog support to open source tools is not considered research. And so my employer has decided to step up and help fund this effort. And because of that is why I kind of ended up in the US and why I ended up at this conference. So SystemVeryLog support in open source tools is what I'm going to talk about. But because this is quite close to what I kind of do in a hobby in this, I have some slides that tell you kind of the relationship between them. You know you don't have a good work-life balance when you have to have a slide like this in your talks. So if it's Google-owned, that's pretty clear. Google-funded means it may have provided some money to it. Google-supported means it didn't provide the majority of the money. So I guess I'm kind of Google-funded because they're not committed to paying me, but I've been there 10 years, but I'm 30 years old, so And the last one's just a project I'm interested in. If you look in the corner, you'll find out about it. And yeah. So the first thing we did is we built a SystemVeryLog test suite because knowing what is actually working is a great way to figure out what needs to be done. And so this is kind of what the test suite looks like. If you ever worked in the browser world, you may have remembered the ACID test suites. This is kind of an ACID test suite for SystemVeryLog-based functionality. At the top, we have a list of the parsers and tools. And so if you're interested in SystemVeryLog, you should definitely, or ASIC development, you should definitely look at these tools. We have Verilog, which was mentioned previously. There's also OSIS, which I think was mentioned. There's also Icarus at the other end, and a bunch of other projects that you might find interesting. Verilog is defined in the LRM. SystemVeryLog is defined in the LRM, which is the language reference manual. I don't think the current version is available, but definitely older versions are available publicly. And so we have unit tests for pretty much every section of the LRM. And then we also have full design tests. So if you've ever been in the RISC-V world, you may have heard of Ariane, that's developed out of Europe. There's also IBEX, which is used by a group called OpenTitan. And then there's the Western Digital Swerve Core, Western Digital really committing, and a few other ones in there. And they're kind of the full system test to check what works. We've also imported other people's test suites. There's the base jump STL, which is if you're doing ASICs and want a bunch of libraries for like FIFOs and clock domain crossing things, the base jump STL library is really good, but it's written in SystemVeryLog, which means you can't use any open source tools at the moment until that line goes green. So just like compilers, you start with a parser. We looked around at what was available, and it turned out there wasn't a good SystemVeryLog parser out there at the moment. So Google released a SystemVeryLog parser. It's called Variable. It's been used internally for 4 or 5-ish years. It's written in Flex and Bison with a special adapter. And this is kind of targeted mainly at code formatting and linting. So it's kind of the equivalent to Clang format. So if you're writing Verilog or SystemVeryLog, Variable can be very useful for formatting your code automatically to a style guide. We also worked with this guy called Alain. He is French. And he has pretty much a full SystemVeryLog parser and preprocessor called Surelog. It's written in Antler, which means it's a multi-threaded plus incremental parser. And it has a lot of features to it, like Python APIs and stuff like that. So the guy called Wavedrom, who does the diagram, actually wrote a tree sitter grammar. Tree sitter is written by GitHub, and it's an incremental parser. It's mainly designed for being used in editors so that you can pass every keystroke as they type. This is pretty cool. And this one came out of nowhere. This was really interesting. Once we had a test suite, a person turned up with a pull request which added their parser and pretty much ended up being the most green on the test sheet and pretty much covers everything on the test sheet. He has a linter, he has a language server. I have no idea who he is or where he comes from. It's written in Rust, so maybe Rust is good for writing parsers. I don't actually know. But yeah, it's very green. So that was kind of cool. The other thing you might have noticed is there was multiple things across the top. And SystemVeryLog looked at what C++ did to C and said, we're going to do the same to Verilog. And yes, it was a very hold my beer moment. So we don't want to have to implement that about 20 times. I would say SystemVeryLog support is kind of like C++ in the late 1990s. If you ever tried to use templating back then, your compiler may be exploded. That's kind of where SystemVeryLog is. So Alain is created this thing called UHDM, which is a universal model that parsers can implement that allows the other tools to talk to it. So you can actually try swapping in Variable or SureLog to pass the parsing side of it, and they can both go into OSIS or Verilator, or at least that's what the hope is. And it's mostly auto-generated using an IEEE standard. I'll not say that VPI is good, but there's at least a specification for it. So that kind of makes it one better than a lot of these existing stuff, which don't even have a specification. And this is kind of what it looks like. There are files written in YAML which describes the various features in the API, and then you get, C files and some serialization out of it, and and then that hooks to this. So this is pretty cool. I don't know much about it because I've somehow become a manager instead of a person who does something useful. So Alan is a person to talk to about how this works, and he's a very productive person. So in terms of styling, well, the first thing you need is a style guide. If you don't have one, go and steal the low-risk OpenTitan style guide. It's actually pretty good. It tells you about all the downfalls of Verilog. Verilog has a lot of downfalls, like C. Who here knows all the undefined behavior in C? Luckily, nobody was silly enough to put up their hand, because they'd be wrong. Verilog is very similar. So as I said, Variable is a code formatter. It currently targets the low-risk OpenTitan style guide, but like Clang, will probably have multiple style guide supports. It has linting as well. It has 37 rules. I don't know what they all do, but again, they come from the style guide. The idea here is to automate away all the kind of checking that humans do normally. SureLog is kind of interesting in they can do design-level checking of stuff. For synthesis, as I said, OSIS is the target. That's still a work in progress. For simulation, we're targeting both Icarus and Verilator. And what about VHDL? Well, Google's an American company, and so they only care about SystemVeryLog. However, OSIS plus VHDL has been apparently working on making it work for microwatt. Maybe you should bug them if you're interested in VHDL. So that was kind of what we're doing with SystemVeryLog. We're hoping to have between 5 and 7 people working on it full time. It's a pretty big task, but hopefully this will help drive forward SystemVeryLog support in the open source world and get professionals and hobbyists back onto a similar set of toolchain. This is all front-end stuff as well, so that feeds both into FPGAs and into the ASIC flow, like what the ERI Summit was doing. And so obviously the people at the ERI Summit were very interested in this because they want to support SystemVeryLog, but currently they can't. How are we going for time? 10 minutes. So I also gave a second talk at the RI Summit. Hopefully, this isn't as new to you guys as it is to the people at the RI Summit. But this is just kind of a grab bag of things that I think you should know about. The first thing is kind of cores and IPs. If you're doing RISC-V on an FPGA, you should be using VEX RISC-V. These are real-world results. These are not theoretical. These are all numbers I have actually seen in the real world with VEX RISC-V. So if you're not kind of getting that type of performance out of your FPGA RISC-V core, you should be reevaluating how good your RISC-V core is. You might notice these numbers are a lot bigger than you typically hear about. And that's because most people have been taking ASIC cores and putting them on FPGAs. When you're designing for an ASIC and when you're designing for an FPGA, there are very different sets of trade-offs. Vectris 5 was very much designed for a FPGA, and this type of performance actually beats microblaze mostly. Microblaze is actually pretty good, but Vectris 5 is like it wins in some benchmarks, loses in other benchmarks. But yeah, you could probably switch to RISC-V now if you're using microblaze as a soft core. If you need DDR, just use LightDRAM. It literally uses a third of the resources that the Xilex one does. And it's awesome. It supports pretty much everything under the sun. We've had it scaled down to 8-bit wide SD-RAM interfaces on the ICE40 up to, an UltraScale Plus board where the chip on it by itself costs, $6,000, $7,000. Same code base. And yeah, it uses a third of the resources of the commercial one. And the Litex ecosystem is all actually pretty good. There's Ethernet, there's PCI Express, SATA. If you ever need to connect two FPGAs together quickly, Light IC Link is pretty good.
So these are all FPGA targeted, not ASIC targeted?
These are all FPGA targeted, not ASIC. They don't have any analog parts. But come and talk to me about that later. Projects. If you haven't heard of Zephyr, I kind of describe it as I wanted Linux, but I couldn't make it fit. Zephyr goes down to 8 kilobytes of RAM, which is a lot smaller than Linux will go. I've seen it in 8K of flash, 8K of RAM type configuration. I highly recommend Zephyr if you haven't seen it. If you want to do an open source security chip, I recommend you check out OpenTitan. I don't work on the OpenTitan team, but the OpenTitan team has been very successful in taking what was traditionally quite a closed system, which is all these gray blocks, and converting it to being a lot more open. If you look at maybe some of the stuff I'm doing, you might notice that some of those gray boxes may not be gray for much longer. And this is the Tomu. If you want one, come and show me that you're not going to put it in a bag and never touch it again. It's got a fully open source toolchain that runs RISC-V. And it runs MicroPython, and it's pretty cool. In terms of tooling, if you're using QEMU, you should stop using QEMU and use Renode instead. Renode is full system emulation. It has a config file format so that you can define your memory map without having to define, a for-long thing. It's modular and text-based. It's 100% deterministic, so you can use it in CI. It has support for running robot scripts, so you can do something like boot Linux, log into Linux, ping a machine that can be fully virtualized and fully tested on CI. And it supports doing things like simulating whole IoT networks. So if you wanted to test how your firmware rollout goes when half your machines are on one firmware version, half your machines on another, they can do that testing. The thing that I was telling people at the RI Summit is most of those people are hardware people, and they're like, oh, you should just Verilate the VHDL. That runs at maybe 1 megahertz if you're lucky. Linux takes a long time to boot at 1 megahertz. This is really cool, though, in that you can take some of your VHDL or HDL stuff in Verilator and simulate the RISC-V in Renode. So only the peripheral, which you're too lazy to write a model for, is being run in Verilator and simulating the HDL stuff. That's really powerful. I hear that they are doing power support because there's now an open reason to be doing power. And even cooler, you can actually run the peripherals directly on the FPGA over this wishbone bus. And so if you have a FOMU, you can actually run a RISC-V and run the software on your computer, talking over the bridge to a peripheral running your FPGA. If you need to interface with EDA tools, you should be using this Python library called EDLIze. Please don't write another Python library for interfacing to EDA tooling. There are about 30 out there which only support like 5 or 6 different EDA tools. EDLIze supports about 30. So we should just all be using that. And FuSock is where EDLIze originally came from. It's kind of described as the apt-get for cores. Like apt-get, it provides no guarantee that the cores you get will do what they say. But if they've taken the time to add FuSock information, it's likely to be slightly better than one that hasn't. So I'd highly recommend looking at FuSock. I believe Swerve has been wrapped in FuSock. I believe Microwatt has been wrapped in FuSock. So yeah. In terms of verification, if you haven't heard of CocoaDB, you should check it out. CocoaDB is really popular among the ASIC crowd. I don't quite know why, because they normally hate things like Python. And CocoaDB is basically a Python driver around your simulator. It's pretty cool. And we did a full USB 1.1 compliance test suite in CocoaDB that you can actually run against multiple different USB implementations, including USB implementations which require software running on a soft CPU. So the USB stack in the FOMU is an example of that. It can be tested with the USB test suite, and it does things like replay a normal Linux enumeration sequence, and a normal Mac enumeration sequence, and a normal Windows enumeration sequence that are captured from real-world examples. And it integrates with Kate Temkins, I think is her name, USB decoding library, so that when the whole thing blows up, you don't go and get, like this random bit in the middle of nowhere is wrong. You actually get a decode which shows you that, the CRC value for this thing is wrong, or you sent the wrong type of token back. So that's pretty cool, and kind of shows the power of CocoaDB because you can integrate it with a lot of existing Python functionality. I'd really love to see a kind of Ethernet equivalent, if people are interested. In terms of documentation, you should use Syncs. Syncs is awesome. And if you need timing diagrams, Wavedrom is awesome. And it has a Sphinx plugin, so you can use Wavedrom in Sphinx. If you need digital diagrams, I find I'm too lazy to draw them manually. So Netlist SVG will create you an automatic diagram from Verilog. And I have packaged it up into a Sphinx extension, which lets you automatically generate diagrams in your documentation from VHDL. And so that was the first 2 talks. The last talk I can't actually give here at the moment, but If people want to come and stand around later when they're not recording, I can give you an update on that talk, which might be titled something like that. But it's that. So yes. So hopefully in the next couple of weeks, that will be more widely available. If you want to come and hear more about that stuff, come and talk to me. And I think that's everything. Do we have time for questions or thoughts or questions? I think people are tired and want to go home, maybe.
You stand between people and Peter.
So a bit of a naive question. I'm really only beginning to play with the open tools now. I'm kind of confused why it's necessary, other than to use existing cores, to have SystemVeryLog in the first place, given that it seems all of the action is in stuff like spinal HDL and.
That would be to say, like, all the action is in OCaml. If you live in the OCaml world, it kind of looks like all the action is in the OCaml world. Spinal HDL is awesome for writing VEX. If VEX wasn't so awesome, though, it being written in a spinal HDL would mean I didn't use it. But VEX is like so awesome, it's too good to not use type thing. It won the prize for the most performant FPGA RISC-V implementation back in 2018. So that was pretty cool. It would be like saying that there is no RISC-V toolchain for C++. That excludes a large portion of the industry. It's kind of like, I don't like SystemVeryLog particularly much myself, but definitely having what the majority of the professionals in America at least use for development, and hobbyists using the same core toolchain set, I think is really important to driving this forward quickly and enabling people to do interesting things in this area going forward. And so that we can kind of show them how to do more interesting hardware, as said by a software guy who has no idea what they're getting into type thing. I have been dusting off all those old arguments that I had in the early 2000s about how open source compilers could actually be competitive. Who here uses a closed source C++ compiler excluding Microsoft Visual C++? I think we've got one, maybe and a half.
Does it count if a platform hasn't been updated in 20 years and it's doing something weird?
That is a very Stuart answer. I'll count it as a 0.1. So C++ compilers, LLVM, GCC. I don't know if you'd use anything else these days. SDCC is kind of interesting. It needs more developers. Its support is kind of patchy. I've used SDC. And so, yeah, if you're interested in that other thing at the end, come and talk to me, and I'll take off my mic and chat to you about it.